Ladies and gentlemen, welcome to Coach Hanik's Vector Challenges. These are some questions you have not seen. They're nowhere in your notes. They're just extra above and beyond. As you can see, there's a special note. It says, special note, try the challenges before you listen to my explanation. So I'm going to scroll to each slide like this and then give you about 20 seconds. I'll read it out loud. Then after I read it out loud, stop it and try it on your own. When you're done, go back and watch my solution here. So it says a plane is headed due west at a velocity of 50 meters per second. For each of the following, draw a scaled vector diagram and calculate the resultant velocity of the plane when acted upon by a 20 meters per second wind that is blowing. A says west, B says east, C says north, D says when is the velocity maximum, and E says when is the velocity minimum. So if you are going to try it on your own, stop the tape now. Okay, so welcome back. Here we go. Let's try this here. Well, it says to scale, so we're going to have to first draw some lines here. And I do have some vector arrows already drawn on the picture here. It might not be perfect, but let's see what happens. So first is a plane is headed due west. So I'm going to take my arrow, point it in the westward direction, and let's see if I can get it to move to the right. I'm having a problem with the thing, so just give me 1 second. I don't know why it won't move. Here we go. And as we go to the right here, I'm going to now move the meter stick here, and let's come up with a scale. So we have 50. I'm going to use 1 centimeter equals 5 meters per second. So my scale is 1 centimeter equals 5 meters per second. And let's see if that will allow us to actually do something here. So we're going to take that arrow. I'm going to go here. This is 50. Since this is 50 right here, I'm going to actually now click on this, and so that means it has to be 10 centimeters. Let's see, that looks pretty close. And then my next one says I want it to be 20 meters per second. So I'm going to take the other vector, and that should be 4 centimeters. So let's see if we could shrink that down a little bit. Is that good? That's close enough. And this one happens to be going west as well, so I have to change that, remeasure that. I have 4 centimeters and 4 centimeters, which is 20 meters per second. Let me write this down here. This is my 20. This is my 50. All right. So next thing I do is move it. This is in a westward direction. The initial one was going west. All right, we know that. If I take my other one and follow a tip-to-tail format, I now know that the resultant is going to be, let's draw the resultant in green here. My resultant equals 70 meters per second. And that's my answer for letter A, 70 meters per second. And now if I was taking my ruler, this should be 14 centimeters, which is correct. So let's go to the next question here. I'm going to erase all of this. Still, the large one is going to be the 51, which is consistent. So I'm just going to slide this down here. And the next one says that B is now going in an east direction. So I'm going to take my vector diagram, reverse it, measure it again. This should be 4 centimeters. And now I have it in this format here. I'm just going to do it slightly above so you know where it is. That would not be in a tip to tail format. I must change that. So I'm going to relocate this, because this center is my one spot is my starting point, and push this right over here just above it so we could still see both arrows. I don't know what I'm afraid if I put it over you might not be able to see it too well. And I know now I'm going to draw the resultant. The resultant is from here, which is my starting point, and I'm going to draw to my ending point, which is right here. If I take my ruler, I get approximately 6 centimeters. Well, 6 times 5 is 35, so I have an answer of 35 meters per second. Okay, so let's erase all this here now. Oops, wrong button. Let's erase this here, and let's get the meter stick out of the way, because the next one says that this one is actually going in the north direction. And so I gotta really change my my ruler right now, and change this again. Come up here. It's a little short, it looks like. That looks much better. I'm going to straighten this out just a tad here. Okay. And I take this here again. If I was to put it right here, that's not tip to tail format. You'll see some examples that look like that. We must move that tip to tail format. Again, if I grab my protractor and bring it right down here, if you remember how to use a protractor, you take the hole right here of the protractor and put it on the origin of the two vectors, it looks like it's a pretty nice 90-degree angle. So I'm going to put this to the side here, and I'm going to move this one in a tip to tail fashion, and then I'm going to draw. Now this one's not going to be beautiful, I could already tell you this right now, and the challenges with this program is that the ruler may not go at this angle. So I'm going to draw my resultant. I'm going to label it R, and I'm always going to put an arrowhead on this. Alright, that's what I'm looking for right now. Well, we can now take the ruler and twist it. Ooh, it might work here. Let's see what happens. And place it up here. It's not perfect. Let's see if we can rotate a little bit more. Oops. Yeah, this will not allow me. Alright, you know what? Let's try this here. Oh, this is very close. So, according to this, it looks like it's just 10.5 centimeters. Well, I don't know if I agree with that, so what we're going to do is actually prove this to see if it actually works. So I'm going to grab the ruler and move it out of the way. And again, my answer was, I think anyway, is 10.5 centimeters. And that would actually mean that if I was to following my scale, it would be 52.5 newtons. I'm sorry, not newtons. I'm a mistake, meters per second. Well, let's check this out. Since this makes a right triangle, I'm going to do one thing right now. I'm going to use Pythagorean theorem. C squared equals A squared plus B squared. And now that I have that, I have a C squared equals 50 meters per second squared plus let's try to straighten that up a little bit here. Plus 20 meters per second squared. I'm not going to bother with you all the math. The answer comes out to be 53.9 meters per second mathematically. Well, that means we're off by let's see here, 1.4. And that would be totally acceptable. Again, I know the diagram on the board did not work out perfectly. I would definitely draw it more accurately. And we were just getting an estimate of 10.4, and you have that plus or minus. If you remember, New York State for any angle gives you plus or minus 2 degrees, and depending on the physical numbers, the larger the numbers, the more plus or minus it is, because every little millimeter changes the answer that much more. So I would definitely say this is an acceptable answer. And now we have both a diagram and the math of the both two, and that's fine. I definitely would accept both answers here. Now I'm going to erase this here. because I want to, I want to go over the last two questions. And the last two questions were, when is the velocity at a maximum? Well, if I could grab this and move it out of the way here, just so I could actually write these things. So it says, when is the velocity at a maximum? Well, if you remember, when we're looking at these, that we had 70 was the maximum number. And let me just explain this to you. So you had 50 meters per second west. And then following the tip-to-tail format, we had 20 meters per second west. And this was at a 0 degrees. 0 degrees really means same direction. There is no angle between the two. And so they're actually working in the same degree. Now, granted, it's going in the west direction. Doesn't matter. If they both were acting in the north direction, that still would be considered 0 degrees because they're both going in the same direction. They're both going in a southeast direction, still 0 degrees. The next question, so the answer is 70 meters per second and or 0 degrees, which gives you that same direction. The next question, though, says, what is the when is the velocity minimum? Well, we already have the answer. It's going to be B. It's there already for you. It's 35 meters per second. But how did we come up with that? So I draw my 50 again. And I now know I'm going to draw my second vector at 20 going back. This is not drawn to scale right now. And then I now know that my resultant is from the starting point to my end point. I ended up right here. I now know the difference is going to be 30 meters per second. And that is in the west direction. And so when is the velocity minimum? The velocity's minimum is when the angle is 180 degrees. Also, I want to apologize here. I wrote 35 up here. It really should have been 30 meters per second. I made a boo-boo there. All right? So that's how we actually solve for those letters, A, B, C, D, and E. Let's try another one. This one says 3 forces are applied to the same point of an object. A 15 Newton force pulls to the east. Pulls to the east, and a 3 Newton force pulls to the west, and a 20 Newton force pulls to the south. Calculate the resultant force, magnitude, and general direction. What is the magnitude of the direction of the equilibrium, which would cause equilibrium? All right, let's do the first part. So I'm going to give everyone 10 seconds to stop and pause this if you want to try it yourself. Okay, welcome back. Here we go. I hope that was 10 seconds. So first, let's just get rid of that. As you can see, here's my box. This is my object. We have 3 forces. We have 15 Newton going east. Let's see here. I'm going to do this to scale. So we have to make this a little larger. 15 going to the east. And then it says 3 Newtons force going to the west. Close. Let's shrink this down a little bit. 3 west. Oh, sorry. This is going to the west. So I gotta go like this. Change it to 3, and I'm going to also go from the same spot. What I'm going to do now is just shift the box a little bit. And then I'm going to just take this off just a tad so just so everyone can see where it is. Okay, so it's kind of going to that one point there. And then it has 20 Newton force that pulls south. So I'm going to do is basically turn this here so I can get a measurement, turn my arrow, move it over, move it over here, extend it to, I gotta go the reverse way. That looks pretty good. So what I'm gonna do here now is just change my entire diagram so you could all see what's going on. Okay, so there's my box, and those are what the three forces look like. And now I know what's going on. I have a 15 Newton going to the east, 3 Newton going to the west, 20 going south. I want to know what the resultant is. Well, first, I'm going to look at all these here and say to myself, well, this 3, if I bring it over here, is going to cancel out part of this right here. All of this will disappear because they're going to subtract each other, which would give me a measurement of 12. And that's critical to understand. So what I'm going to actually do is redraw this one here, and I'm going to erase all this now. And I'm going to say to myself, this I'm going to remove. I want to redraw this one so it's 12. And now I have we're dealing with 2 vectors, because the other two, again, the 15 and 3 subtracted each other. They didn't cancel each other out. They subtracted each other, and now I have a total of 12 now. Well, this is not tip-to-tail format, so you have a choice. I'm going to show you both. A, you could move your 20 south, and this doesn't look perfectly straight. I'm going to just try to straighten this out a little bit. Your 20 south that way. Okay, going back to the original diagram, you have another choice. You could actually move it up if you want to do that. Or what I'm going to do here to make my life a little easier is draw and put it over here. And the reason I'm doing that, this way it allowed me to actually do the math over here. And so, just so you could actually see what's going on. And now, let's get this a little tighter here. Again, if you were drawing this to scale, it's going to be much better. And now I'm going to freehand this. I know it may not work out beautifully. Let's just try one fell swoop. Oh, look at that. That's beautiful. All right, let's get the result in here. Again, I know that this is 12 newtons. And I know that this was going to be 20 newtons. And I have an overall direction of east. I have an overall direction of south. I want to know what this is. So let's see if we could actually do some math here. First thing I realize, it's a 90-degree angle there. I'm going to actually do Pythagorean theorem. So we have c squared equals a squared plus b squared. C is what we're looking for. A is going to be 12 newtons squared plus 20 newtons squared. So we have c squared equals, I believe I got 544. And that's going to be newtons squared. Take the square root. And C gives me an answer of 23.3 newtons. Now this said general direction associated. So that's my magnitude. I'm putting a check mark. Solved. 23. So R equals, what happened there? Equals 23.3 newtons. Now I'm looking for my general direction here. All right. Well, if I put a compass anywhere on this, I know that's north, south, west, east. If I relocate that compass to right here, there's my north, south, and I'm looking for this general angle here. Or I could use the other one. This would be theta x off the x-axis. This would be theta y. I'll extend this a little bit here. That'd be theta y. The question is, which one do you want to use? Well, I have all 3 segments right now. I have my 90-degree angle, and that's all I got right now. The one thing I would probably do is use part of SOHCAHTOA. So I have to erase some stuff here because I know there's just too much going on here. So I'm going to erase this right here, get the equation out of the way here. And let's go back here. So I would say that sine theta equals opposite over hypotenuse. And so my sine theta is what I'm really looking for. And I could put the x there if you want. Oops, that's x. And my opposite is going to be 20. And that is newtons. And my hypotenuse we solved for was 23. And so my sine, actually I don't, you could do all the math. My theta x, the angle off the x-axis, comes out to approximately 59 degrees. And so this would be 59 degrees right here. And that does make sense. It's not drawn perfectly, I know that, but I know it's greater than 45. I can clearly see that by looking at it. And so it does make sense to me. So I'm going to add that now. I'm going to have to just do a little racing here because we're kind of running out of room. So let's see if I can get rid of this here, and let's add that now. So I have 23.3 newtons at an angle of 59 degrees. And now, for some of you who are not sure what's going to go on here or how we do this, this is how I figured out. If I walk along this axis, which happens to be my east axis, and I stop and have a pawpaw, most of you love the pawpaws, but then I want to get to the resultant line, I must go in this general direction. That is south of the east axis. So I have to write south of east. And so there's my final answer. Now the last thing it's asking for, it says, is what is the magnitude and direction of the equilibrant? And the equilibrant is equal and opposite. So let me just erase some things here. So here we go. E for the equilibrant equals 23.3 newtons at an angle of 59 degrees. Well, this time, if you focus back on the diagram, the equilibrant, it's drawn. It's not drawn to scale here. It's too. I don't want to go off the board here, but it goes up in that general direction. We know that this is the west axis here, so it's in that west-north axis here, and so that 59 would translate right here. Okay, and so that would be north of west. Because if you walked out here, you'd have to go up, which means this is the west axis, okay? You'd have to head up, you'd have to head north of west to get to the equilibrant. And so now we have two answers there. Let's check out the next one. A plane is flying 20 degrees southwest, measured from the south axis at a speed of 100 meters per second, is blown by a 45 meter per second west wind. Calculate the plane's resultant velocity. Okay, I'm going to love this question only because I don't have to use the protractor and ruler. And I'm going to move the protractor and ruler. Even though you could draw them to scale and measure them, I'm going to save save some time here. So first thing I do, I know that this plane is flying 20 degrees southwest. So if I were to come here, actually, let me do this differently. Let's do this instead. Let's do my horizontal line. May not be perfect. We get the idea. First vector, 20 degrees southwest, measured from the south axis, which means that this is my 20 degree angle. This is my vector. It is going to be 100 meters per second. Is blown by a 45 meter per second west wind. I'm going to pick a different color. Well, I know directly west, if you forgot your coordinates here, I know this is going to be a horizontal line. It is not drawn to scale. I know that, so I'm going to say 45 meters per second. My resultant is in the general direction of this way. Clearly, it is not drawn to scale. The 45 is almost the same size as 100, so it's not drawn to scale, but we get the idea. So the first thing I would do, I'm going to erase just a little bit so I have some more room here, because you don't need to see that side of the equation, or diagram I should say. I'm going to use law of cosines. Now, by all means, my check would be to draw this to scale and measure it with a ruler or protractor to see what happens. But I choose to do this. So I'm looking for C ultimately, which is our resultant. All right, I can put this equals C. A is going to be 100 meters per second. That's squared. And you know what? I think I'm going to do this. I'm going to just leave out units here because I'm running out of room. I don't want this to get crazy. Plus 45 squared minus 2 times 100 times 45. I didn't want that to happen, but cosine, and now we have to put an angle here, cosine C. Cosine C means if this is going to be C here, it's the angle opposite, which is this angle right here. And so let's see here, if we had 20 degrees, see, this is where the diagram would come into hand because I could just measure the angle. Okay, I'm going to skip this entire question. I'm going to have to come back to this one because I think it's going to take much longer than actually what I thought, and I don't want to spend too much time. All right, so I'll come back to number 3. Sorry about that. That's really annoying to me. All right, let's try the 4th question, and I'll have to come back to make a whole special YouTube video if it's needed. So if you want one, just email me, and I will, no problem, make one. I just don't want to waste the time on this because it's getting pretty long anyway, this video. All right, number 4, a person walks 3 miles north and then walks 15 degrees northwest, measured from the north axis for another 4.5 miles. Calculate the person's resultant displacement, including the direction, including the directional angle. So let's see what happens here. So, actually, you know what? He's going north, so bad way to put the diagram because he's walking north. So I'm going to start down here. And so walks at a 15 degrees, 3. This is my 15 degrees right here. And then, oh, sorry, I apologize. I read it backwards here. Let's do it all over again. It's okay. This is why we learn here. We do this here. I read it wrong. He walks 3 miles north. And then walks at a 15 degree at a northwest, measured from the northwest axis. North axis. So here's my north axis, and I'm going to measure. That's my 15 degrees, and this happens to be 4.5. And so I'm now going to draw my, see here, resultant. The arrowhead's going to be right here. I'm looking for R. Again, using Pythagorean theorem. Law of cosines. I know, first of all, I'm going to need to know angle C, which is located right here. A straight line is 180 degrees. 180 degrees minus 15 degrees, which is right here, if you're wondering, equals 165 degrees. So that's the angle C. So let's see what we got here. C squared equals A squared plus B squared minus 2AB cosine C. This was going to be 3 squared. Again, I'm leaving out units. Plus 4.5 squared minus 2 times 3 times 4.5 cosine 165. Solving for C, doing all my math, I get an answer of 7.1 miles. Now I need an angle. I need a directional angle. My suggestion is we use this angle right here. Okay, we have the law of sines for that. I'm going to erase the law of cosines here, so we can definitely get rid of this. And then we have sine B over B equals Sine C over C. Sine B is what I'm looking for. Sine B happens to be right here. We'll call that B, angle B, over the opposite, which is 4.5. Okay, what happened there? Equals sine C, which we solved for at 7.1. I'm sorry, wait. I think it was 7.4 to be honest with you. I might have wrote the wrong thing down there. And sine 165 degrees. It's not working out great. All right, here we go. I'm looking for B. I get B to be 9 degrees. So my answer is going to be 7.4 miles at an angle of 9 degrees west of north. Not a perfect box, but you get the idea. All right, I really want to go back to that one question, though. Yeah, it's just too complicated with the diagram I drew. So I'm going to move on past that. I'll make another YouTube video. All right, hope this was helpful. If you liked it, please comment on it. Let me know.